You see that when your company were to test a material, they always go for what? Tensile, tensile. Why? The sample is easy to prepare, the equipment is more readily available. That's the only answer. Okay, you can design in twist, in shear, it costs you more. And the estimation of 130 and 150 is not so far away, so it's what? It's okay. Okay, so now, so for this case, we have to determine what is our principal stress and maximum stress. Then we can come to the what? To the material properties over here and see, okay, what material to use and what is the factor of safety. Can anyone tell me what is the factor of safety that is normally used? Can anyone tell me? Anyone? What is the norm value? I look at the chat now. Anything above 1. You're right. Okay. Anything above 1. So the thing now is this. You can use a safety factor of 10. Okay. You can use a safety factor of 1.5. But what does it actually mean? Safety factor of 10 means what? Anyone? If we were to put a safety factor of 10, what does it mean? It means there's a lot of uncertainty, a lot of things you don't know. My mom can design a structure with a safety factor of 10. Okay. Safety factor of 1.5 means what? Okay. There are a lot of things that you can foresee. Okay. The only thing that you cannot calculate is like impurities of the material. Okay. Impurities of the material that maybe sometimes the steel that we're going to buy, construction steel, has a lot of impurities. I don't know what to use. Okay. I know the use strength can be plus or minus 20 megapascal or 50 megapascal. That's where we are not sure. Okay, so 1.5. Safety factor of 1 is pure arrogance. Okay, it's like you know everything and anything. It's like the Titanic. It will never sink. Yeah, right. Okay, now coming back to here. So so I will write for you two formulas. Okay, I'll write for you two formulas. Okay, that we're going to use to analyze this. Okay, so we are going to calculate the normal stress. Okay, so by looking at the structure, our normal stress. Okay, so we are going to calculate our normal stress. So our normal stress will be equal to PZ over A. Okay, it can be plus or minus MY over IYY multiplied by Z. It can be plus or minus MZ over IZZ multiplied by Y. Okay. No, this is wrong. I'll tell you why it's wrong, because it's no more in Z. Okay, so this is MX over IXX multiplied by Y, and this one over here is in X. Now, why that is the case, it is all dependent on our transformation. Okay, and I'll tell you how to define the transformation from this diagram over here. Okay, right. So this is one set of formula that we are going to use. Okay, and then the other set of formula that we are going to use is shear. Okay, it's going to be shear will be equal to Vx over Iyy, right? Qy divided by T. Okay. Or we are also going to use Vy over Ixx Qx T. Okay. So there are two sets of formulas that we're going to see. Then after we have determined this, okay, we are going to apply more circle. .3D. Okay, so I'll leave some space, okay, to write stuff. So I taught you this in week 1 and 2, right? This one is now for this case it's going to be thin wall analysis. Or some of you like, oh, you know what's the surprising thing? Okay, y'all did really well on thin wall and thick wall question. Okay, bending moment and moment are the same thing. Okay, yeah, it's just the moment is force times perpendicular distance. Bending moment is force times perpendicular distance. So this is week 3 and week 5, right? And over here, this is week 6 until week I think 9 or 10, right? And this is week 11 and 12. Okay, Alex, there you go. Okay. I know you say, I thought you say only what's after the term test. Yes, but it's an integration things to do proper design, unfortunately. Okay, right. Okay, so this is the breakdown. That's why you have to like it's the integration where students have a lot of problem. Okay, not just you guys, everyone. I teach civil engineering department, mechanical, everyone has this problem. But you guess what? This is the most important thing that you're going to learn. Okay, right. So let's start that. Okay, so in order to do this, okay, so first we have to I'm going to do a side note. Okay, so the first thing to do is to define the transformation. Okay, so that how to define the transformation. Okay, so the book has already did it for us. They call it X and they call this Y. Okay, if it's not given, the best thing to do is to follow this. Okay, is to follow that. Why? Because we need all this information over here. And all this information are relative to the data that is given to us. Okay, we need all this information. We need area, we need everything. We are not going to calculate. We need everything. Okay, so given that the horizontal and the cross section is X, and then this is Y, we do the same over here. Okay, so this is X and this is Y. So if we were to follow that transformation, now we have to label where is our X and where is our Y. Okay, so this direction over here, right? This will be defined as our X. And then the other direction over here, this will be defined as our Y. And finally, using your right hand rule, this direction going up will be your Z. Okay, so as I said, define your transformation first. That is very important. Okay, that is critical. So this question asks us about point A. Okay, what is our stress state at point A? Okay, and this beam over here, you can see that this is a white flange shape. Okay, so we know that we have to apply thin wall analysis. Okay, you do thick wall, we are in trouble. Okay, we have to define thin wall analysis. Then from here, okay, we write down our values first. So the beam that has been selected is W200 by 41.7. So this is the beam that has been selected. Okay, so if you were to ask me, how can this situation play out for you? So, for example, the loading is given. Okay, decided to use this beam. Your task is to select the right material. Okay, so what material to use? Should you use structural ASTM A36, or should you use standard ARSI 302, or reinforced steel, medium strength or high strength? Okay, just to give you a bit of scenario over here. So if that's what we're going to use, so we know that our I-axis, so it's less confused now. Okay, so because we follow the transformation, we know that our I-axis is equal to 40.8 times 10 to the power minus 6 meter 4. And we know our IYY is equal to 9.03.
Why is it 10 to the power of minus 6?
Because if you look at the top over here, it's in millimeters to the power 4, right? So it's millimeters, right? So I bring it to meters. That's why
Okay,
times 10 to the power minus 6. Okay.
Got it. Yeah.
Then our area is equal to 5320 times 10 to the power minus 6 meters squared. Okay. So all these are given. We know it. Now, later on, this information we will need. Okay, like the 205, 166, 724. Those information we will need later on. Okay, so this is what we know. So now the second thing that we do, okay, so define the transformation we done already. Okay, second thing we do is determine the moments, torque, axial force, and shear force. Now, this is one of the most critical components. Okay, if things are done wrong, everything goes to the toilet bowl. Okay, like what I taught you before, you have to view this if necessary. You have to view at XY plane. You have to view on the YZ plane. And then you have to view on your XZ plane. Okay? You have to view on the whole trigger. Not just determine, and also make a remark on the loading for the elements. Okay, so over here, we are only going to focus on element A, but I will do both. Okay, I'll do both element A and element B. Okay, so here we go. Okay, so I'm going to copy this diagram. I'm going to paste because I need it to help me to do my analysis. Okay, I'm going to make it small. Okay, so the first thing we're going to do, we are going to look in the, so this is my transformation first. I'm going to look on the XZ plane. Okay, we're going to look at the XZ plane. Okay, we're going to look at the XZ plane. So now we sketch the XZ plane. So this is my X, this is my Z. Okay. So there will be, I'm going to sketch the structure. Okay. So this is our structure.